Well, good morning, everybody. And see, Rob. Good morning, everybody, and welcome to the 2023 MEI Symposium. My name is Michael Breer. I'm the director of the Melbourne Energy Institute, MEI, and I welcome you all today. Of course, before we formally start proceedings, I acknowledge the traditional owners of the land on which we meet. We've got many of you coming from other parts of this beautiful country, specifically South Australia and Adelaide, where our opening plenary is journeying from. But I welcome you all here on the lands of the Wurundjeri people, traditional owners of this land, and we acknowledge their elders past and present. So MEI Symposium, we've been running this for quite a few years now. I think we ran the first one in 2017 or 18, and they've gone pretty well. We always like to open with, a distinguished speaker who can talk to us about particularly topical matters. And this year we have Graham, or Gus as he's known to his close colleagues, Gus Nathan from the University of Adelaide and the HILT CRC. We do intend, though, that the MEI Symposium is really about promoting the graduate students and the postdocs and the early to mid-career researchers at this university. So whilst we're very appreciative to have Gus and other keynotes across the day, and we thank you all for coming and sharing your insights and expertise with us, we also really wish to emphasise how important the workers at this university are, the students, the postdocs, the lecturers, the senior lecturers are, to producing the best scholarship in energy-related fields that this university has to offer. So in advance of everybody's talks today, our guests and also our own staff and students, thank you all for coming along. Now, Gus Nathan. I think Gus and I met in 2001, and Gus was probably an associate professor or something like that, and I was a lecturer or whatever it was back then. And we were two mechanical engineers working in combustion and thermodynamics, and so we've worked together in various forms over the years on different things, primarily through what's called the Combustion Institute, which is the body that people like us and chemists and chemical engineers and others, the scholarly association, I guess we'd call ourselves, that does research on combustion, and we've done a lot of work together over the years with other people at Sydney and UWA and elsewhere. Gus works in heavy industries. We now call these hard to abate sectors. 20 years ago, Gus was working in hard to abate sectors, but it wasn't quite so sexy then to work in hard to abate sectors like cement production. And then little facts like steel making and cement production are the two largest sources of greenhouse gas emissions from industrial processes globally. So Gus has been working in this field for decades. And thankfully for people like Gus and maybe like me and some others, people have realised that these things are really important, hard to solve, not easily electrified, although many of them can be electrified, but not easily electrified, and yet at the same time very substantial contributors to global greenhouse gas emissions and also economic productivity. So steel's number one in terms of global greenhouse gas emissions from heavy industry. Cement's number two. Number three is aluminium.
Yeah, there's a step down with a number of them.
And paper is, well, it's falling, but paper's falling for very obvious reasons. But plastics broadly, I think, is number 4 or something like that. So today, Gus is going to be talking about hard to abate sectors: steel, cement, aluminium, and he's working with companies in the heavy industries in the HILT CRC that make steel, cement, aluminium, and other things. So there's a grand challenge that CRC is trying to help solve, and that's a grand challenge that for a country which is the largest iron ore exporter in the world, a substantial, very substantial alumina and aluminium exporter, and a land with a lot of renewable resource and other such things, this kind of work that Gus is talking about today is, of course, key to Australia's global environmental footprint, but also our our economic well-being. So, without further ado, please welcome Gus, and thank you all for coming along.
Thank you very much, Michael, for the kind introduction, and it's great to be here. As you say, we have had a long association together and also had some discussions yesterday, keen to build those partnerships as well. So I'm going to talk about some of the prospective pathways to decarbonise heavy industry. It's a general term, but we're particularly focusing on the three that Michael mentioned. And I'd like to also, firstly, add my acknowledgement to the Wulto people here and also the Ghana people from the Adelaide Plains where I come from, and also to acknowledge the other contributors to this presentation. In the HILT CRC itself, I've listed the program leadership team here, whose names are shown. Some of those are from industry, some are from the other research community, and also going to talk about some of the work from the University of Adelaide, and some of those contributors are also shown there. So a few words about the HILT CRC. It's a 10-year funded program, and the main objective is to ensure a prosperous heavy industry at the forefront of the global low-carbon transition, and particularly to de-risk these emerging pathways that will be needed to keep the sector economically competitive. These are some of the partners in the CRC. You'll see companies like Adbri in cement, Alcoa, South32 and also Rio Tinto in lime, and then Fortescue, Grange, Liberty and Roy Hill are in the iron ore and steel sector, together with the other research partners. Melbourne's not a partner in this, but we're keen to find some other partnerships particularly in tackling the energy partnership in future steps. So that would be looking forward to doing that. The Centre for Energy Technologies that I'm from, actually we'll be holding a research day, not unlike this, where we also promote the work of our own researchers, but we hold some other forums here which are focused externally. The High Temp Forum is one that tackles this high temperature industry process. The HYPED Forum is hydrogen production technologies, looking at some of the emerging platforms to potentially lower the cost of hydrogen on a technology agnostic basis. ISF is pyrolysis-based routes, and it shows some of the activities. I won't go into them in detail, but we're keen to explore opportunities to work together in those areas, so hoping for discussion later. So this is really the topic that we're interested in, and the one that Michael alluded to. What this is showing, this is some data from the International Energy Agency showing globally the three sectors. The blue is electricity, green is buildings, this orangey colour is the transport, and then industry is the light brown. So currently industry is around about 30-ish%, but you'll see that as this sector decarbonises, going forwards projected to 2050, these are of course projections, they're not predictions, but because industry is the one that's expected to go most slowly, its relative share gets bigger. And so these red dots show the relative share, and you'll see by about 2040 it's projected to be over 40%, simply because it's one of the slowest to abate, and there's lots of reasons for that, including being capital intensive, not being enough commercially available systems at the moment. And so this is why it's a challenge. Also, the timescale is where research can contribute, although it's really important that technologies be demonstrated at approaching commercial scale by about 2030 if they're to be rolled out by 2050. So this is the kind of challenge that we're working on. Despite the challenge and the cost, this is a diagram I really like from Mission Possible, some work in Europe, illustrating although the relative cost is big, compared to the final market, it's still quite an achievable cost. So this shows, for example, for steel and cement, for steel to decarbonise by the currently known green steel routes, or the best known routes, it would be projected to add on this scale about 50% to the cost per tonne of that product of steel. So you can see 50% addition, you might say, well, that's a very big impost, will it ever work? But on this scale, what it shows is by the time that gets to a higher value product, such as an automobile, it would only add 1% to the cost of the automobile. That's because of all the downstream value adding that goes in that process. So fundamentally, this is what's driving the transition. Now, of course, that won't apply to every vehicle, but if, let's say, companies like BMW say, well, we want to introduce a premium product that we make a net zero car, for example, it's not going to apply across all their industry, but there's a part of their sector that will pay that amount. In the meantime, as it gets going, that relative cost of 50% might come down to 25, and the premium, becomes a smaller premium to bigger share, and eventually the whole lot goes that way. That's kind of what is projected to be the key drivers. And the same for cement, and plastics is the other big component, which is a very high relative cost, but in a bottle, by the time it gets into a plastic bottle, and some of you have already seen, there's some carbon neutral drinks emerging on the market. So in terms of heavy industry in Australia, this is showing some basic calculations of the energy consumption of some of these main sectors in Australia. This is not electricity, this is total energy, of which the majority is non-electrical. It's mainly things like coal, for example, or depending on the sector, coal or gas, but mainly fossil fuels directly burnt. So you see in New South Wales, of course, is the biggest steelworks at Port Kembla, uses just over 110 petajoules per year. That's compared to the grid, although not exactly the same because this is electrical, you see it's about 44% of the New South equivalent in energy terms of New South Wales grid. In South Australia, it's a smaller plant, less efficient, but it's roughly equal to the scale of that grid. Alumina is actually the biggest energy consumer in Australia. In Western Australia, you'll see there's about over a gigajoule, 1,000 petajoules per annum, and that corresponds to 8 times the Western Australian grid, and in Queensland it's about 6 times. So very, very large energy consumers in scale. Now, of course, if they were to come with a net zero energy source, be it electrified or be it another form of hydrogen, for example, or another source, however it gets there, this is the scale of the challenge just for our current processes. And of course, those processes could grow. So working with our industry partners, we've developed a few scenarios that are plausible. Not saying this is what will happen, but these are some indicative scenarios of how much impact this could be. So for example, in South Australia, there's a big magnetite resource. Currently, there's about 1.2 million tonnes per year of steel made, but there are plans on the market for not yet commercial, but they're plans for potentially 30 million, a factor of 30, not of steel, but of a direct reduced iron kind of product. This wouldn't happen overnight, but the kind of scale of that is then you see this would be equivalent to approximately 94% of the whole NEM in terms of scale. Likewise with alumina, if we were to do some conversion of about 40 million tonnes per year of some of these net zero products, this would be not the whole plant, but that's about 35% of the NEM. In the Pilbara, if you were to upgrade 20% of Western Australia's iron ore to a green DRI, that would be 5 times the NEM in terms of energy scale. So this is indicative of the scale of these impacts. Now, cement itself is a relatively small energy user. However, if 2 of these plants, the CO2 was to be captured and converted to methanol with the hydrogen, well, that also is still about, you see, about a gigawatt of energy. So a very significant scale. That's about the size of the South Australian grid on average. So any of these plants you see would have big impacts on whichever we're going to do on a net zero process. So the energy challenge is big. So which are the prospective pathways? And generally it's expected or projected that all of these different routes are prospective. Probably none of them is going to do everything. There's going to be, hydrogen is expected to be important, particularly the iron ore, because it's the closest to market in the reduction phase of these net zero options, although CO2 capture and storage is another one that's also prospective. So, but importantly, you look at these, this is saying for iron, steel, alumina, cement and lime, you'll see that most of these are at pilot scale or sub-pilot scale. And electrification is, particularly in the iron stage, is one of the earliest stages, which is why the electrification route for the iron making process, even the developers or those that are using like the electrolysis route are projecting that maybe by 2040 they'd have a commercial demonstrator, whereas hydrogen commercial demonstrators are already in planning for well before then, in the this decade. So biomass, of course, is important, but limited availability. But a component, CO2 capture, and whether it be storage and reuse is also being considered, particularly in the cement industry. But again, we don't have commercial scale in any of these processes yet. So they're all different options, and hence the sector is saying, well, on the one hand, we need to have the energy available. We don't know what the cost of these options are going to be. They're also not yet commercial. So we need to help to de-risk that. That's what this challenge is about. So indication of one of the projections, again from the International Energy Agency, for the mix of technologies that are likely to, that they're projected to be significant around in the iron and steel globally. And you'll see that the electric arc furnace only does the steel making part of the process, but then you'll see that there's in this case, the hydrogen is expected to be a significant component. In this one, you see the green hydrogen is these orangey ones here. So typically, hydrogen is projected to play a very significant role in that transition, and direct electrification is not expected to play a big role by 2050 for this sector. It could be in alumina, but again, it's not yet commercial. So we have the commercially known route of electrolysis. I just would want to mention that there's a number of these other platforms which are close to commercial. Some of them are closer than others, but the solid oxide electrolysis, the key advantage of this is that the electrolysis is being done with steam. So therefore, the latent heat of vaporization is already undertaken, and there's enough sources of potential low-grade heat in these high-temperature industrial processes that potentially steam could be generated from the waste heat to then offset about 25% of that energy process. Of course, the variability of the energy, any variability in the electricity would then need to be managed as electrical storage rather than as thermal storage, but nevertheless, that's one of the prospective routes. This system is actually quite well advanced because work has been done on the fuel cell side of it, where there's gigawatts already in production. The methane pyrolysis route, I talked about that in more detail yesterday. I won't go into much detail today, but I will mention this is the route where methane is pyrolyzed into solid carbon and hydrogen, at least not necessarily completely solid carbon, but carbon rich, predominantly carbon. And this is potentially two products, and this is what's driving it, and also about a quarter of the enthalpy of the water splitting route. So there's a commercial demonstrator. This is from a company, Monolith, in the USA, who have got $1 billion loan from the US government to build 10 times of these plants under the new US investment schemes. And there's also other things a bit further from market, but nevertheless a lot of investment in lots of platforms. This is just a few of them. All of the technology platforms have investment. This is one being developed at the University of Adelaide by Greg Meether and his team with a lot of partners, showing some of the emerging photocatalysis routes. So you just say, well, one of these technologies by itself may be a low probability, but when you put them all together, there's a significant probability that there'll be emerging hydrogen technology platforms together that will then start to contribute to lowering the cost over what is already being done. Just a couple of words about the methane pyrolysis technology we're working on. Some of this work has been done in partnership with the Future Fuels CRC. We're working with Simon Smart and his team at the University of Queensland. This is showing a salt and metal combination. The salt is floating on the top, and then again in a beaker, the carbon particles floating on top of that. So the concept is that the methane, which may be natural gas or it could be biogas or a blend thereof, is bubbled through this reactor, and the carbon, because unlike a solid catalyst where the carbon will coke the solid catalyst, in a liquid phase floats to the top, and then the idea is it can be separated, and we've got some work we're involved in this. This is showing one of our reactors, which is not quite commissioned yet. We've had quite a few delays with getting certification, etc., but it's hopefully will be commissioned the end of this year. In the meantime, we've been doing other work on that system that I won't go into in detail, but it's one of the routes which is prospective to the advantage of the bubbling media, of course, is they have high rates of heat and mass transport. Greg's work that he's been working on is to increase the efficiency of radiation into the water splitting reaction, and again, one of the ways to do that is to turn the liquid water into the gas phase, and that is also a way to harness a greater fraction of the energy. And he's been there's a company a company that Spark, which is working in commercialisation, also with the support of FFI, and so they're targeting 15% solar to hydrogen efficiency and have got some significant scale demonstrators in progress. So that's a little bit about some of the energy sources. We talked about some big numbers in terms of energy demand for our net zero processing. But it's important to remember that as we go to 2050, we're not just saying we need to put the same energy in, but now with, say, hydrogen. We're not simply going to replace the equivalent number of petajoules of of coal with petajoules of hydrogen, because this sector is going to continue to evolve. And we think that to make it viable, we've got to also have a step change in performance of this sector. There's lots of opportunities to reduce energy consumption by being more efficient and more effective, and I'll explain how some of those ways can be, including by better industrial ecology or increased connectedness between these processes, taking what are currently waste streams and recovering them, and this can have significant potential to lower those costs and do it better. So these are some of the processes within the HILT CRC we've been developing the conceptual framework for, and we're starting to put some numbers on some of these connections and work out which ones are most prospective for our particular set of partners. So in the iron ore phase, the beneficiation is a phase of separating the gangue or the impurities from the ore, and currently this is done for magnetite using the magnetic magnetic properties of the magnetite ore to help remove the gangue. But it's still very energy intensive because you have to crush it up very, very fine. It takes a lot of energy to do that, but it's not currently applied to other ores such as hematite significantly, and also is not applied also into the bauxite route. But we think there's potential with some next generation beneficiation technologies, if you can separate things up front, you can lower the total energy cost. So we've got a couple of platforms in that area, but also we want to make use of these other materials in the gangue or in the co-products. Now, of course, this is also something that's been developed previously, but if we can do this stage more effectively, it opens up new doors for bringing things like supplementary cementitious materials, which is this green line here, to displace some of the cement products. Also, you'll see there's potential to recover because some of these these ores have got water chemically bound to the ore. such like goethite ores, and recovering some of that steam can also be an energy opportunity. Likewise, recovering steam, I'll say a bit about in the section. Recovering steam is currently vented from the calcination process, and this is an energy component to recovering this back into the digestion. Typically when people talk about the cement sector, they talk about cement alone. Lime is not usually calculated so much as a sector entirely in its own right, because lime is often embedded within the other industrial processes. So like a pulp and paper plant, we usually have a lime plant stuck away in the corner, and the same with iron plants. Some of them will procure it, but often it's separate. So it's not aggregated. But limestone obviously has got CO2 chemically bound. It's a carbonate ore, and if we're going to decarbonise that is connected. It's a common process to cement and lime making, but it also feeds into a chemical feedstock into both alumina in digestion phase and in the iron and steel making process. So this is another really important process, and we think the CO2 capture and reuse, or whichever pathway, is critical, particularly for that sector. Even if you've got rid of all fossil fuels, you have to manage that. So which are some of these opportunities to lower the cost from these net zero sources? You'll see this is an example of how we think things can be done better if we do net zero routes. So currently, in most of these reactors, like the calciners in alumina and cement, these processes are burning fuel with air. So obviously, this is something, Michael, I'm sure everyone who works here in combustion, this is stuff that you know for hundreds of years. But when we burn the fuel, your product is some CO2, some water from the hydrogen and the hydrocarbon, and nitrogen is the biggest component from the air. So this means whatever you're producing is diluted with nitrogen and these other components. On the other hand, if we replace it with either electrification or solar thermal, or if we were to burn hydrogen in oxygen, we don't have any nitrogen anymore. And particularly where you have an ore which has got an OH chemically bound to it, releasing steam, if you're now going to burn this in a steam atmosphere, you can recover that steam. That's not just water, which is obviously a constrained resource, but it's the latent heat of that vaporization, which is energy. So this is why, if we were to electrify these processes, we can potentially have a big impact on the net energy by recovering this steam and making use of it. Could also be used in a solid oxide fuel cell, such as the thing I showed in the earlier example. So in alumina processing, I'll show you how this is very, very important. And alumina, remember, in Australia is our biggest single energy consumer. So this is one of the pathways. There's different potential routes, but they're broadly similar to this. We have a digestion process, and this takes the bauxite, which is alumina trihydrate. It's got some iron oxide, which is the contributor to the red mud, and it's got other components, including clays, for example. So you want to separate out everything except the alumina trihydrate to put into the calciner, and then you make alumina oxide, which is what goes into the electric arc furnace. So you want to do this separation of these materials is this digestion system, which from an energy perspective, the thing to know is we need steam. So steam is currently made from a steam generator, combined heat and power, which burns fuel and air. Steam is generated here and is diluted in the nitrogen, as per demonstrated previously. So this steam cycle is about 2/3 of the total energy of the plant. And then it's vented. On the other hand, this chemically bound water, OH, in the calciner is heated to drive off that in the form of water, and that water is also vented because it's diluted with the nitrogen, which makes it hard to recover. So what we'd like to do is recover this steam and bring it back to here. Then you don't have to burn as much steam here if you could do it. Of course, it's not completely trivial because there's particles in there and there are different pressures, but conceptually, if we could do that, the estimates are that we could save This is the amount of steam in these processes. You can see that potentially you can supply half of the water, or even more than that, through this recovery process, which would greatly reduce the steam demand. And of course, steam could also be generated from different sources. Doesn't have to be done by this route that's there now. So what we'd like to do is introduce a recovery system. This is shown as a box, but there's of course new engineering that would need to be done to do that. This is one of the things we're tackling in HILT. You have to do particle recovery, have to balance pressures, etc. But nevertheless, this could, we estimate, with even allowing for losses, etc., that at least 25% of the total energy to plant could be saved by developing the engineering systems needed to do that. You'd still need to make up water. But this means, as we plan for a 2050 target, we've got to know what's the new plant looking like. We don't have to know the numbers exactly, but if we know we're going to be recovering a lot of that energy, we don't need to supply all of it. In fact, we can potentially reduce our steam requirement by at least half because you're recovering that energy. So this is the kind of opportunities that we can get. So been working on this topic for quite a few years, and the first thing is what happens to the alumina itself when you calcine in steam rather than in steam being only a fraction of the atmosphere. How does it impact on this material? Because actually you're doing a back reaction of removing this OH. So if you're putting it into a pure steam atmosphere, it's going to inhibit that calcination reaction. So we've done a lot of work. I won't go into that in detail, but briefly summarise a snapshot of some of those results. The loss on ignition is effectively the inverse of conversion. If you've got this, you take the material after it's calcined, you heat it again, and you can see if you can reduce any more weight. And that's called a loss on ignition. So effectively, a loss on ignition of 0 is 100% conversion. So this is smelter-grade alumina, which is what is needed to be met to go into a commercial plant. And this is the specific surface area. So you can see that in running in steam, we can potentially get the 100% or the high concentration of steam is this black line here. We can potentially achieve a higher specific surface area for the same loss on ignition, which is better quality. So far we haven't demonstrated this in an actual reactor. We've demonstrated in lab scale steady state processes, but this is our next phase, is to confirm it. Potentially you can lead to a lower temperature. There's a number of other advantages in going this route that can lead to net energy savings. So we've done a lot of process modelling, and I won't go into all the details of that, but just to show you a snapshot of some of the results, what we have here is the energy cost per year. If this plant was to be run with hydrogen and oxygen in that calciner, so you're running it in steam, this is the break-even cost with, this line here is current natural gas costs. This is natural gas at $12 a gigajoule, without even a CO2 price in there. And you'll see that that once you get down to natural gas at $16 a gigajoule. So you see once you get down to hydrogen costs of, this is 2, 3 and 4 Australian dollars a gigajoule, that you're starting to break even when you can get the energy consumption net down to about 2, which is with some steam recovery. It's plausible. Then you can be breaking even if you're even with a hydrogen cost of $4 gigajoule, which is a bit below what we are now, but not that far below. Then you would be breaking even with for example, a natural gas price of $16 gigajoule. This is before putting in a carbon price. So it shows there's potential. We're doing more work on this techno-economics, which will be published before too long, but it demonstrates potential. So now we move to iron ore, and talking around some of the challenges from the Australian ore context, particularly in the Pilbara. And one of the key challenges is that majority of Australian ores from the Pilbara are below the grade that would be needed to go into the commercially proven route of the ore that can go into the is suitable for direct reduced iron. So there's potential, and you'll see the thing about putting gangue into the electric arc furnace is that the energy consumption goes up in the electric arc furnace. This is the key barrier to running with higher. So the current these ores are not suitable for the commercially proven route, but of course there are emerging routes that could be prospective. This is the challenge. So for the hematite goethite ores, which are in the Pilbara, there's a need for either the ores are too grade for this commercial route, so there's a need for either improved beneficiation technology to get the grade up without too much cost, and or for alternative processing pathways to allow these high gangue materials to be processed in other routes into the net zero, into the green steel pathway. Magnetite ores, they can be done with commercial technology, but it's very energy intensive and adds to cost. And can we do it better and also recover the gangue? So for example, if in South Australia we were to be putting a factor of 30 on the amount of magnetite we're processing, that means, because magnetite is about 30-ish% iron ore, that iron oxide, that means the rest is gangue. So suddenly you've got huge quantities of tailings ponds and gangue, unless you can find something useful, a saleable product. So these would be products which would limit what can be done with those systems. And of course, the energy infrastructure is also why I'm here to discuss that, because you're doing a lot here in Melbourne. This is, we're keen to understand how to also meet that challenge for the energy infrastructure that will be needed. So a couple of the projects, we've been doing some work to compare some of these different processing routes, including the electric smelter rather than the electric arc furnace, with fluidised bed, for example, routes. We're looking at some alternative flash reduction technology. This is actually a company who's got a plant here in Melbourne. I understand you work with them in other projects, Calix, and also their head office in Sydney. We're doing a beneficiation technology I'll say a bit about. So this is a bit about one of the beneficiation routes that we're working on. Conceptually, conventional route, what happened is the iron oxide with the gangue is put into a pelletizer, and then that goes into a blast furnace. And I put in different colours here, right? The oxide is the brown colour, and in the blast furnace, because you melt everything, the impurities come off in the slag. They float off easily, so you can separate and you can handle all the gangue because it's melted in that phase. But of course it uses coke, and that makes CO2. And the coke can be diminished to somewhat with some biomass, but you can't fully eliminate the metallurgical coke from that process very easily. For high-grade ores, this is the kind of process that's been developed in Sweden. If you've got very high purity, like a magnetite ores, the high-grade ones, this can take the same route, but you don't melt in the reduction doesn't melt it only reduces it. And then the electric arc furnace, if you've only got a small amount of impurities, can handle that in the electric arc furnace. When you've got higher concentrations of gangue, this is where we can either potentially put more pre-treatment in to remove some of that gangue, and then it can go through the same route, or you could do other routes such as DRI. You could also put it into electric smelter furnace. There's different pathways. But the idea is if we can remove some more of that gangue, it makes it more suited to commercial routes or other pathways. So the option for thermal pre-treatment of ores, there's been a lot of work being done over the years. Many of you may have been, some of you may have been involved in it yourself, things like microwaves, and all of these have shown that you can put energy in and it can help to soften some of the gangue material, etc. The challenge is that with traditional routes you end up putting in more energy in the thermal treatment than what you save in the grinding, etc. So that's been the real barrier. So what we've been doing that's different is using high flux heating rates. So that means you can heat the material for much shorter. These previous systems would heat it, and because you're processing large material, and they'd be in the reactor for hours, which then takes a lot of energy. But if you can use high flux and the right particle size, you can reduce the thermal energy input. Also use heat recovery, and that is the key step that's different. And also, depending on the material, if it's like a goethite, in that process you can also liberate the OH. if you're doing it in the right atmosphere, you can also recover that steam, and the goethite liberation can add some other benefits to, for example, can improve some of the downstream processing steps. 10 minutes. So, without going into it in detail, we're anticipating in the eventual systems that these will be on a very large, high temperature belt, and so you can process potentially 1,000 tonnes an hour in some of these processes. So these we've been doing work on under a lab scale of putting it under a high flux heater on a small scale system and showing some of the benefits of reduced grinding energy, hematite conversion to goethite, and high surface area if you choose the right temperature band. This is also compatible with some downstream processing that I won't talk about. I'll flick through some of these things. We can talk about them down the track, but we've done some techno-economics on this, and it does look prospective, but I won't talk about it in detail now because we're short on time. But some of the other projects which have been done is some work on fluidised bed. This work is Tom Hunnions from University of Newcastle is driving this stuff, also looking at some of the stickiness properties. We've got a big program looking at how to address stickiness and other material properties of these different gang materials, not just for fluidised bed, but also for flash reactors. So the flash reactor is one that's under development. As I say, there's a company here in Bacchus Marsh dropping particles through a heated reactor tube. So the advantage of this system is potentially can be heated electrically, so you only need the hydrogen for the reduction, and that can potentially reduce hydrogen consumption. So we're doing a lot of work on that process as well that I'll be happy to take questions or discussion later, but I won't go into it in detail now. But just showing some preliminary results, showing that preliminary trials at pilot scale have demonstrated good, but quite good conversion rates, and hence we think this is a technology with some potential, and we're doing work to continue to evaluate it. In terms of work to recover the gang, there's one of the things of interest is that most of these bodies of material have got clays embedded, and clays have been identified around the world as being one of the prospective supplementary material to displace about half of cement clinker. These have got OH chemically bound, so it's another opportunity to recover the water. So we have active programs in that again I won't talk about in detail now, but happy to talk about down the track. I'll just say a couple of words about this concept, because I know in this, particularly at a research-intensive university like in Melbourne, and we talked about some of this again yesterday, but we think there's big opportunities to improve understanding and numerical models such as computational fluid dynamics through better access to a combination of new data with things like laser diagnostics as part of it, but also looking at new spectroscopic methods to understand how these materials are processed, combining it with emerging tools such as machine learning or deep learning kind of processes to start to understand in these new reactor environments, get better predictive capability. Those of you who have been involved in high temperature processes in the past will know that typically most processes have unexpected hiccups. When the upscale, you suddenly get to different regime than where smaller scale work was done, systems get sticky, performance doesn't meet specifications. So to overcome those challenges, we need a step change in predictive capability, and I know you're doing CFD, and so we're also working on this area and would be keen to look at ways to work together to improve our data sets and understanding in that process, and that's an area that we're working on and keen to continue. One of the measurements that we've developed, which is applicable in these large reactors, is this method, which is suitable for in situ particle size measurements, so you can detect in a reactor in situ if agglomeration and stickiness is occurring. So this is called microshadography, and what happens is you have a backlighting system. We've used typically an LED array, but it could also be a laser, and this shines through a particle stream. In this case, we tested it in this particular paper against a falling particle curtain. So this is fairly optically thick, but we also use it in a bigger reactor. I'll show you in the next image. So what happened is the light goes directly into the camera, and the camera has a very short, because it's a micro focusing, has got a very narrow depth of field. So that way, everything you can see in this image, some of these particles are in sharp focus and some are blurred. So those that are in focus, the depth of field is only 0.5 millimetre. So everything that's out of focus, you can eliminate by image processing, and you can remove the ones that are forward or out of the plane. So this shows here a sharp focus particle that's 0.5 millimetre in front or behind. One that's in focus, you can then just reject the others. So then you can get a direct measure of particle size in situ, and the image typical down to about 10 micron per pixel, so you can resolve the shape of a particle as well. So we actually tested this in that pilot scale reactor in an operating high temperature condition, and showed that we were able to get this is our measurements compared with conventional sampling methods, got good agreement with some differences due to the different techniques. And so this is another way of kind of the emerging techniques. This could be used to give much more data than historically has been able to be done, but obviously it's not the only method. We're keen to collaborate to get as many of these new kind of methods as possible to help to provide the step change in understanding of these new reactor systems to meet the challenge. Also doing some measurements of residence time in reactors. Again, I won't go into in detail, but these are the kind of systems we're keen to collaborate on to accelerate more predictive modelling, which is needed to de-risk these systems. So in conclusion, the net zero transition for these industrial processes will definitely impact very significantly on energy systems. They're very large centres of demand which run nearly predominantly, most of the loads are steady state at current. Some may be varied, but it's big advantages in keeping them steady if we can. So these are already comparable with current electrical grids and likely to grow. Each of these processes is bespoke, and there are different ways that potentially they could be decarbonised. Maybe it could be electrification, could be hydrogen, alternative fuels and CCUS. Each of these across the sector are likely to be important, and exactly how much we have to evaluate. But we also have to remember that the future processes will differ significantly from the current processes. There's opportunities to improve them. If we're going to accommodate higher energy costs, we have to improve performance to make them viable. So things such as the steam recovery, we think has potential for at least 25% saving in processes like alumina, and we need to better understand those opportunities in the other processes as well, but also opportunity for new co-products from the gang, different electric arc furnaces with new slags, tailings. These offer opportunities also for mineral carbonation, these kind of products. Some of those will have energy demands as well, but overall they'll be a saving. So technology development is needed because all of these systems are still pre-commercial. Some of the emerging ones are also in the energy supply systems, potential for cheaper hydrogen systems, for example. But there are many prospective pathways that are under development, including those that HILT is working on. I just gave you a snapshot of some of those in iron and steel and alumina, including beneficiation, steam recovery, co-products, etc. But of course, R&D to lower the costs and accelerate this is vital, including the improved predictive tools, and we're very keen to explore cooperation and collaboration to help meet this need to accelerate the decarbonisation of the Australian sector. I'm happy to take questions if we've got time. Thanks, Michael.
So there is, of course, time for questions. It's an important part of things. So anybody with a question? I've got a couple myself, but please, it's more about you than it is about me. Come on, there must be plenty of questions. Yes, sir. Maybe mention your affiliation if you wish.
Yeah, no worries. Tristan Ashford, work for Pollination, but then also involved here at the university. Question about a lot of your processes and the efficiencies that you were talking about all relied on steady state or fairly integrated processes. On the energy side, there's a rule of thumb that if you want cheap energy, be flexible. So how do you see it playing out, the interplay between heavy industry processes and reliability and that continuousness of them, compared to what is going to be the new energy sector of cheap is variable, and if you want constant, you're going to pay for it.
Yeah, this is exactly one of the challenges, right? So we have a big focus on how to integrate variable energy sources into these processes, because you hit the nail on the head. And I mean, these processes, of course, all processes do have some components they can vary, and they already do, right? I visited, for example, Liberty and some of these processes during the big power fluctuation prices in South Australia, for example, but also around the country, where they've got operators sitting there all the time working out which things they can turn off. But things like grinding systems, etc., are relatively easy to turn down, and they do. But things like these thermal processes many of them have got high thermal inertia. So turning, for example, a cement kiln can take 3 days to reach thermal equilibrium. So, and an aluminium smelter doesn't turn off for 10 years. So they can turn them down for periods, but then also the point is that these processes run with small profit margin and very high capex. So what happens is if you reduce production a little bit, your economic viability can change a lot. So for example, one of the processes I worked on, we were able to save fuel consumption by 3%, and that doubled the profit margin. So variability is a very different game in heavy industry. Also, product quality changes with turn down because of their very finely tuned systems that are not easy. So the question so if processes process fine particles, they're much easier to turn up and down quickly than those that process bigger particles. We've got a thermal constant of the material. So that's another driver for potentially shifting to some different types of reactors by the future. But also there are big reasons as to why you want to put storage or other ways into the system. So if you can accommodate things like thermal storage, which is lower cost storage, it may be more attractive than electrical storage. So this is the point you raise is a very big one. Is not a simple answer, and it's definitely, for heavy industry, is a bigger challenge to turn up and down, and currently we've got a project to better evaluate some of those questions and work out how much turn down can be accommodated. Because obviously all these plants want to run at lowest cost, so the cost of electricity or energy will change and there'll be a new optimum, but I think it's still going to be many significant drivers to maintain stable operation for key components.
Good question, and a big one. It's one of the reasons why we call it hard to abate.
Exactly.
Anyone else? Yes, sir.
My name is Robert, the lead on from the podcast Climate Conversations. What's been the most significant change in direction in your research in the past decade?
Well, I mean, I guess in the last decade, heavy industry decarbonisation was a dream. Not a commitment by industry. So we run the High Temp Forum, and the first of those was in 2018, and industry at that stage was interested in. They said, we've got to decarbonise, we want to do it, but no one was committed to it. The Japanese had Nippon Steel there. They said, well, our company is projecting net zero by 2100. By 2020, about half of the companies had then signed up to net zero targets. By last year, every company had signed up net zero targets, and the thing is, their investor demand is requiring that they do it. This is even before the government set any schedule. Now the government has also, of course, legislated costs that will come with that. So this has been a fundamental driver in now causing it to go from being a topic of interest to a priority.
Any more questions? We'll ask from the less usual suspects, Professor Batterham. So Professor Hill from Monash University.
Is this on? Yeah. David Hill, Monash University. This is probably a hard question or an easy question, but I took a photo of that early slide of yours about the emissions across transport, heavy industry, electrification, and And I see decarbonising as a matter of having the technology kind of at scale, but then also the willingness to pick it up and use it. So transport, electric vehicles are there, but they're not fully available for us to buy, even if we wanted to. Electricity, the government has a target of 82% by 2030. All kinds of issues delivering that, but it's kind of possible. But in the heavy industry, what's a timeline? What could we be hopeful for like getting 80% decarbonised? Is that a decade, 2 decades, 3?
Yeah, look, great question, and this is exactly why it is one of the wicked challenges that's been identified. So generally, what we're targeting is to have demonstrations at large scale by 2030 of systems that are prospective to be doing. Generally, the target is we need to be demonstrating by 2030 at large scale. So for example, the steelworks at Port Kembla have just relined their blast furnace. That's a 20-year time cycle for a blast furnace reline. So that gives an indication that that is just being relined. So that means it's not going to be replaced till 2040, right? So 2043 or whatever, approximately. So that's an indicator of why we need to get things demonstrated, because obviously they made that decision based on their commercial decision of what's available now and what they could do by the time this one came up. So we have to have things demonstrated and proven for that time. But of course, we also want to be demonstrating some of the opportunities to improve performance to then lower the barrier for investment. So these also, we need to be also working not just at that scale, but also at the pilot and the earlier scale to be continuously improving these processes and integrating not just, what can be done now, but implementing progressive improvements into it. But we need to be doing, some large-scale demonstrators by 2030. That's the target.
Thank you.
That's a good question and answer to end on, I think, about the timelines. Look, thanks, Gus. Terrific. Great talk as always. And thanks, everyone. Please welcome, thank our guest. And